Hello, my name is Jim Fields, and I've been in analytical graphics for 22 years now. And the past couple of years I've been focused on this area: test, training, tactics, and exercises. And today's discussion is going to be geared towards national defense, though it is really applicable to anyone who is concerned with protecting space assets from threats, whether those threats are incidental or intentional. So why should we care about space threats? Well, we all know that modern threats exist, whether they are obvious kinetic threats like a direct descent anti-satellite weapon, or more subtle tactics like close proximity operations for intelligence or interference missions. So whether it is a compromise in secure communications or a loss of service or even the loss of a platform, our modern cultures have come to depend on space-based assets, and any of these losses would have a serious impact. So we have to understand the threat. The US outspends China 4-to-1 in space, yet China is closing the performance gap. Clearly, our current tools and our approach to space training is insufficient. We need to find better ways to address these threats. In the age of Google and Amazon Prime, relying on 20-year-old software and multi-month training cycles in defense of critical assets is just unsatisfactory. So a military cornerstone is train like you fight and fight like you train. Here at AGI, our former naval flight officers can attest that that is the way it's done in the air community. If they didn't stay current, they didn't fly. And if they didn't fly, they were back in the sims. And they had the right tools to do this. They trained in simulators that were functionally identical to the aircraft that they fought in. And this is where we have to get to in space. So based on the conversations we've had across the market and with our customers, and based on the exercises that we've supported, like Global Sentinel, we have identified two main challenges. First, our Air Force group commanders know that their training tools aren't perfect, and they're doing the best they can with the tools that they have. But it takes weeks to months to generate the data that they need to run an exercise. And this extra time costs more and leads to lower readiness levels. If you're only training monthly instead of weekly, you can't stay current. It also means you can't keep up with evolving threats, and slow tempos are not viable if you're trying to rapidly execute potential what-if scenarios, which is crucial to tactics development. So frequent training is critical, but inhibited by and made costly with today's tools. A second significant challenge is accuracy. Any pilot walking into a simulator expects it to behave like the real aircraft, and yet today's space data simulators use simplistic representations of the real thing. They often model only a portion of the catalog, and typical exercises include less than 100 objects. And that orbital data for these objects is passed around based on the assumption of perfect sensor coverage and perfect orbit determination. Whereas in reality, operators have to deal with up to 20,000 background objects. Sensor data is often sporadic and noisy, and the quality of OD solutions really depends upon the quality of that sensor data. So this kind of unrealistic training without real-world fidelity leads to poor preparedness. So it's with these challenges in mind that we laid out a set of requirements for an ideal test, training, tactics, and exercise support tool. Any viable product had to have scope. It had to handle the majority of the regular threats and space events experienced today. It had to be realistic, employing full fidelity force modeling. Timeliness, it had to be fast. It has to be quick. Again, you can't model what-if scenarios and expect to make progress if you're waiting days or weeks between runs. We want to create a scenario, run it, learn from it, change it, and run it again within minutes. To accomplish this, we need to have automation. We need to take the person out of the loop as much as possible, and we have the automated tools to do this. Of course, security is a key concern in the places that we work. And finally, interoperability is a very big component. It's very important. Many of our customers have their own formats and their own tools as well. And so we envision an ecosystem of tools, each with different strengths. For example, one tool may excel at comms modeling, while another tool may excel at low thrust trajectories. So we wanted a tool to bring them all together into a coherent scenario, and one that was built flexible enough to interact with any format of any of our customers. So it was with these product requirements in mind that we took the next step, and we generated a product here at AGI called SEG, which is our space event generator. So some of the capabilities of SEG are that we can create multiple types of space events, which we're going to talk about in a few minutes, in all orbit regimes. We can have individual or linked sets of events. And a linked event is where one space object is involved in a series of sequential events. So for example, a space object can be launched, do a maneuver, go into proximity operations around another space object, do more maneuvers, and then go perhaps conjunct another satellite. And SEG can solve for the intermediate maneuvers that are required to go from one event to another event. These events are combined into scenarios. So one scenario will contain a multitude of events for a variety of objects that you're interested in looking at a given time. With SEG, outputs are observations, which are generated from sensors. It outputs ephemeris, and it outputs sensor in-views. These observations that it produces can then be fed into a flight dynamics system or a catalog processing system. And ephemeris can be viewed directly in any tool that can handle ephemeris. So SEG supports planning, training, testing, and exercises, and it includes a user-friendly user interface, as well as web services for integration. So SEG meets the requirements for scope by supporting 12 different space event types: reentry, proxops, deorbit, rendezvous, breakup, conjunction, deployment maneuvers, orbital intercept, which is co-orbital ASAT, launch, and the next two events that are coming up will be direct descent, anti-satellite, and docking and separation. So SEG has a user-friendly event workflows, which allows an operator, not necessarily an astrodynamics expert, to build these events and build a scenario and create a set of linked events. SEG is timely. It includes full force modeling or full fidelity modeling, and time independent, where when you create a scenario with a series of events in it, you can move those around as you need. So some of the use cases that are supported by SEG are, the first is a operator procedure training. So if you wanted a checklist for an operator where they're going to, you're going to generate data that shows that a conjunction has been predicted, your operator needs to figure out, how do I respond to that? Or maybe they first figure out, how do I detect it? And once I detect it, how do I respond to that? And so you can use SEG to create that situation happening, and it will generate the data for you, or generate the ephemeris predictions to show that that's going to happen. And then your operator gets that information and has to deal with it. Next is the day in the life operations training. This could be where your operator just follows a checklist of daily values. They get observations coming in that have been simulated by SEG, and they have to process those observations, get their orbit determinations, and go through their checklist of all the different products that they need to make on a daily basis. System performance tests. This could be something like you load in observations in batches to get the orbit determination process, or to test your orbit determination process, and compare the OD results that you get from your process with the truth ephemeris that SEG has generated. A proof of concept study might be something like adding more sensors into your scenario and seeing what objects are tracked more with those sensors and how your OD changes as a result. Simulated over live. So SEG is generating simulated data. If you have historical observations that you also want to process in conjunction with those, you can create events to lay over your actual real historic data. So SEG can also be used to support exercises, do mission planning, and what-if tactics development. So tactics development might be, when can I perform a maneuver that I can either see when I want to see it, or perform a maneuver that I want to try to keep hidden from a sensor network that somebody else is using. So the TTX workflow the way we envision this TTX workflow is that you start off with an operational database, which contains a catalog of objects that you've been maintaining. And these catalog objects each have a state, and there's usually a sensor network that's used to process the observations that are generated for these catalog objects. And those sensors have properties and measurement statistics, measurement types, and measurement statistics associated with them. So we take a snap of a database which contains all of your process data up to some time point, and that's what is used to initialize a seg run. So on top of that database, we build a scenario in seg where you define events, you define sensor cadences, and a sensor cadence, which we'll get into more detail later, it basically results in a definition of how many observations are going to be generated by a sensor network for each of the objects within an event. The next thing we do is define a set of background catalogs, and there's no limit on the number of background catalogs that can be added into a scenario. And these background catalogs, again, are coming from this database that has been cloned. So the next step is to generate the scenarios, to run them to process data, or to create data, and this will create observations and the ephemeris. And once that is done, this data will be stored in the database, and then that can be exported and used. So the observations and ephemeris can be exported for use in like space situational software system or any other TTTX environment that is under test. So this is the seg data flow. The user would start through our web-based user interface. And we see over here there's a set of events. No, it's hard to see on this screen. We'll get into this in a little more detail later. There's a CZML view that shows a visualization of what's going on. The user defines data for these user-defined events through the user interface. And this data is going to be stored into a database. And the database, again, we've talked about, contains sensor models, sensor locations, measurement types, and measurement biases for each sensor. It also contains the database will contain the initialization data, which came from that database snap. And that's the states for the different objects in the catalog. So once you build a scenario and you add events to your scenario, all of that information is stored in the database. Then we have a process that runs to generate data. And again, this whole interaction between the user interface and the database is controlled by services. So through those services, we're going to run this generation engine, which is going to create observations, create ephemeris, and create new states for the various catalog objects. So this is our scenario landing page. This is in our user interface. Basically, this is showing that we have, in this case, 6 different scenarios that we've created on this system. And each scenario, you can give it a name and a description. A scenario has a time span, an analysis time period, over which data will be generated. And you can see on the right side over here, there's details when a scenario is highlighted that it just has the scenario name and the data associated with it. And you can, once this particular scenario is being processed currently, generating data, and once it is finished, you'll be able to view the output and go look at the data that is created. So SEG has 12 different types of space events. You can see on the right side over here, catalog, conjunction, decay, deorbit, and I'm not going to describe each and every one. But space event is really either a space object performing an action, like a space object can perform a maneuver, or for instance, a deorbit would be, you would tell a satellite that you wanted, or you create an event where a satellite is going to deorbit either over a given region of the Earth or at a particular time, and SEG will compute what the maneuver is required to create that deorbit trajectory. There are also, so that's a single space object type of event. There are also events that include multiple space objects. And in that case, like a proximity operations event is where one satellite is going to act on another satellite by going into relative motion around it. And again, SEG computes the maneuvers that are required to achieve this relative motion. And each event that's in SEG has a sensor cadence that's defined for it. And again, we talked about that the sensor cadence is what dictates how many observations are going to be generated for each of those objects within that event. And again, these observations are what a sensor tracking network is going to produce as data that would then be fed to an operator to process if they're doing orbit determination. Another type of event that we have is an ephemeris event. And the inclusion of an ephemeris event with SEG allows operators to incorporate more complex missions when needed. So without trying to build overly complicated workflows to meet every situation in SEG, we allow an astrodynamicist to come in and figure out a very complicated trajectory. And that's really what this value point is that whatever tool you have that can generate ephemeris, we can pull that into SEG and use it. And that ephemeris can also even be linked with other events within the scenario. Another nice thing about the ephemeris event is it can be moved in time. So you can take a historic trajectory, like say you had a launch from 10 years ago. If you know what that trajectory was, you could move that forward and play it now against your current set of catalog objects. So this is a sample event workflow where through the user interface, I'm going to create an event, a conjunction event in this case. And as an overall summary, this top section is really common to each of the event types, where you're specifying an event name, and after you define the event type, and a description and some other data. And as this event type changes, the data that's displayed down here is updated, and it's custom for each of the event types. So for this conjunction example, you're specifying what the primary object is. And that's the satellite that's going to have a conjunction done to it, basically. We pick what time this conjunction is going to happen, and then we're inputting data that's relative to that event type. And for this specific conjunction event, you're defining the relative geometry of the two objects at the time of closest approach. And below here, we're defining what the secondary object is. And so SEG has the ability to either create simulated objects to participate in an event when needed, or to use an existing catalog object and maneuver it in order to achieve the results of an event. And so for this case that we're showing here, we're creating a new simulated object, and we give it a name and we define the characteristics of it. What's not shown on this page, if we could scroll down, but we can't, is that there's a sensor cadence definition under this. And that is for this event. Again, we're defining how many observations are going to be generated for each of these two objects in our scenario. We also have a catalog event, which is a somewhat unique type because it really consists of a grouping of objects. And the reason they're grouped is because they're all going to share the same sensor cadence. So each of these objects in this catalog event are going to have the same number of observations produced, if possible, by the same sensor network. So yeah, each catalog has a unique sensor cadence. And so since each group is using the same sensor cadence, if you want different objects to have different cadences, you can create multiple catalog events. There's no limit on the number of catalog events you can have. So you might have a certain set of geos that are grouped together, and maybe another set of geos, or high interest objects grouped together as a catalog event. And in each catalog event, there's really no limit on the number of objects that you can include. And what this really allows us to do is have a fully realistic background catalog. And it allows the trainer or the exercise planner to adjust the difficulty of the scenario. The more catalog objects you have in the background, the more observations are going to be fed into the system. So sensor cadence, mentioned this a few times. This is how we determine how many observations are going to be generated for each object within an event. So the sensor cadence it defines the number of observations that are produced by specifying how many tracks per day are going to be generated for each of these satellites. So each track has a set of observations, and a set of observation sets, really. So the number 1 here could refer to a right ascension and declination measurement. So there's some time between successive right ascension declination measurements, and then you could have a track and 20 minutes later have another track. So that's what this revisit time indicates. What we do is, given the locations of the sensors and the constraints on each sensor, we compute all available access intervals between the sensor and each space object. For those, we subselect a set of intervals to meet these cadence definitions and generate observations over those intervals. And again, these observations include the measurement biases and the measurement noise is expected for each of these sensors. And so that gives the number and the quality of the data allows the trainer to direct the control of the difficulty of the scenario. And this allows modeling more realistic uncertainties that we talked about in the requirements. So SEG is built on a service-oriented architecture. So this means our services are interacting with the back-end database, which is Oracle. The processing of data is actually automatically distributed using SDK scalability. We provide a fully documented API. We have support for both REST and SOAP services. It's completely automatable, and for security, we have web service authentication and authorization provided with AGI Identity Platform. SEG uses a similar hierarchy to our systems toolkit in that we have scenarios which govern the simulation environment. So a scenario contains a series of events and other data, and those events generate ephemeris. And actually, a scenario can be viewed in SDK by being able to download a visual data file, or VDF. So there's interoperability from SEG into SDK. And once SEG generates data, this data can then be fed into an exercise engine of your choice, whatever system it is that's under test or being used for the exercise. So to train like you fight, you need a tool that will quickly generate data that's as realistic as possible. And that is our goal with SEG, to support test, training, tactics, and exercise missions. Thank you very much.